Quantum teleportation has long been considered a concept of science fiction, often imagined as a futuristic way of instant travel. However, recent breakthroughs in physics are making teleportation more real than ever. Scientists have achieved quantum teleportation, transferring information over vast distances without a physical medium. This is not about moving objects or people from one place to another, but about transferring data and quantum states. Dr. Michio Kaku, a leading physicist, has revealed that quantum teleportation is no longer theoretical. This technology could revolutionize communication, computing, and even space travel. But how does it work, and what does it mean for the future? Understanding quantum teleportation requires diving into the mechanics of quantum entanglement and how it challenges conventional physics. Unlike traditional teleportation in science fiction, quantum teleportation does not physically relocate objects. Instead, it transfers information about the quantum state of a particle to another distant particle. This process relies on quantum entanglement, a phenomenon where two particles become intrinsically connected regardless of the distance between them. When the state of one particle is measured, the other instantly adopts the corresponding state, even if they are separated by thousands of miles. Einstein famously called this spooky action at a distance because it defies classical physics. Scientists have successfully used this principle to teleport quantum information across laboratories and even into space. By using entanglement, researchers can transfer the properties of one particle to another without transmitting any physical matter. This ability to instantly transmit quantum states is the foundation of quantum teleportation and has major implications for computing, communication, and security. Recent experiments have proven that quantum teleportation is not just theoretical. One of the most remarkable breakthroughs occurred when scientists successfully teleported quantum information across a distance of 1,200 kilometers using the Chinese satellite missions. This was a major leap, proving that quantum entanglement can be maintained over vast distances. Another milestone was achieved by researchers at Fermilab, who managed to teleport quantum states through fiber optic cables with near-perfect fidelity. CERN and NASA have also conducted experiments demonstrating quantum teleportation over increasingly long distances. These breakthroughs confirm that quantum information transfer is not only possible but reliable. Each of these achievements brings us closer to practical applications of quantum teleportation in real-world scenarios. These advancements suggest that future quantum networks could replace traditional data transmission systems, leading to faster, more secure communication methods. One of the most immediate applications of quantum teleportation is in cybersecurity. Traditional data transmission involves signals traveling through cables or airwaves, making them vulnerable to interception. Quantum teleportation, on the other hand, does not send physical signals. Since quantum information is teleported via entanglement, any attempt to intercept the data breaks the entanglement, making eavesdropping impossible. This principle is the basis for quantum cryptography, which could make hacking virtually obsolete. Governments, financial institutions, and intelligence agencies are particularly interested in quantum encryption. A fully developed quantum internet would allow for secure global communication without the risk of cyber attacks. This level of security would have enormous implications for industries reliant on encrypted information, including military defense, banking, and corporate data protection. Quantum teleportation is also expected to play a crucial role in space exploration. One of the biggest challenges in deep space missions is communication delays. It takes about 14 minutes for a signal to travel from Earth to Mars, making real-time conversation impossible. If astronauts were to explore distant planets, this delay would increase dramatically. However, quantum teleportation could eliminate this issue. Since entangled particles communicate instantaneously, it could enable real-time communication between Earth and Mars. This would revolutionize space exploration, allowing mission control to interact with astronauts without any lag. Additionally, this technology could enable rapid data retrieval from distant probes, making deep space exploration more efficient. NASA and other space agencies are actively researching how quantum networks could be integrated into future space missions. The idea of teleporting humans remains purely theoretical. However, in principle, if the quantum state of an object could be fully mapped and transmitted, it could be reconstructed elsewhere. This concept raises complex scientific and ethical questions. The human body consists of trillions of atoms, each in a precise state. To teleport a person, every atom's position and energy state would need to be recorded and transmitted without error. Even if this were possible, it introduces the dilemma of identity. Would the teleported person be the same individual or just an exact copy? Would consciousness transfer, or would it create a new being with identical memories? Scientists are nowhere near answering these questions, and current teleportation experiments only involve particles at the atomic level. While human teleportation is unlikely to happen soon, advancements in quantum mechanics continue to push the boundaries of what is possible. Quantum teleportation also challenges fundamental concepts of physics. Einstein's theory of relativity states that nothing can travel faster than the speed of light. Yet, quantum entanglement allows information to be shared instantaneously between particles, suggesting that the universe may operate on principles beyond classical physics. This has led to new theories about spacetime and the nature of reality itself. Some physicists propose that quantum entanglement could reveal hidden dimensions of the universe. Others believe that understanding quantum mechanics at a deeper level could lead to new forms of propulsion, possibly even faster than light travel. As experiments continue, quantum physics may force scientists to rethink some of the most established principles in modern science. Countries around the world are racing to lead in quantum technology. The US, China, and Europe are investing billions into quantum computing, cryptography, and teleportation research. China has already demonstrated quantum teleportation through satellites, giving it a potential advantage in secure communications. The United States, through institutions like NASA, MIT, and Google, is working to develop practical quantum networks and computing systems. Private companies like IBM and Microsoft are also competing in the quantum race, hoping to commercialize quantum computing for broader applications. This global competition is expected to drive innovation at an unprecedented pace, bringing quantum technology closer to mainstream use. Maintaining quantum entanglement over long distances is difficult because environmental noise can disrupt the connection. Current experiments require extreme conditions, such as ultra-cold temperatures and vacuum-sealed environments, to prevent interference. Additionally, quantum computing technology is still in its early stages, limiting how much data can be processed and teleported efficiently. Scientists are developing new materials and techniques to improve stability and reliability. If these hurdles can be overcome, the potential applications of quantum teleportation will expand dramatically. As with any powerful technology, quantum teleportation raises ethical and security concerns. If governments or private entities monopolize this technology, it could lead to unequal access or even misuse. Some experts worry that quantum teleportation could be weaponized, enabling new forms of cyber warfare. The scientific community is calling for international regulations to prevent misuse and ensure that quantum advancements benefit humanity as a whole. At the same time, quantum teleportation challenges philosophical ideas about identity and reality. If one day we could teleport people, what would that mean for our understanding of consciousness? Would teleportation create an identical person, or would it destroy the original? These questions, while speculative, highlight the profound implications of quantum mechanics on society and ethics. Quantum teleportation is no longer just a concept, it is a rapidly developing technology with the potential to revolutionize communication, computing, and space travel. Recent experiments have proven that quantum information can be transmitted over long distances with remarkable accuracy. This breakthrough could lead to unhackable communication networks, real-time space communication, and possibly even new understandings of the universe itself. While teleporting humans remains purely theoretical, research continues to push the boundaries of what is possible. As nations and private companies compete to develop quantum technologies, the world is on the verge of a scientific revolution. Quantum teleportation is not just about transferring information, it is about reshaping the way we understand reality itself. The question is no longer whether quantum teleportation will change the world, but how soon it will become part of our everyday lives.